Here's a problem involving forces. Here's the situation. We have a 2,500 kilogram tractor towing a 1,500 kilogram sled full of rocks. The coefficient of kinetic friction of those rocks, of that sled, is against whatever the surface is, pavement or whatever, is 0.3. Now, we have the owner of the rocks. The owner is got his heels dug in. I didn't draw the owner in a very good posture. The owner would actually be kind of leaning back and has his heels dug in. Coefficient of friction of 0.8, trying to hold the sled back. Now, the owner is big. The owner has a mass of 250 kilograms. That puts the owner in the giant category. The owner is over 500 pounds, about 550 pounds. And so that's a significant owner with a significant coefficient of friction. Maybe some good rubber-soled shoes on to provide a good coefficient of friction. Is the owner going to be able to provide enough to hold the tractor back? Now, I haven't specified what the coefficient of friction of the tractor is. The problem might well be to find the coefficient of friction of the tractor necessary to succeed in pulling these rocks and its owner. The way I phrased the problem, though, is the tractor wants to accelerate at 0.7 meters per second squared. If it doesn't accelerate that fast, this owner, who's kind of slow but very big, will be able to overtake the tractor and cause mayhem to the owner of the tractor. So what we want to do is, let's begin by finding the tension in this rope here. Okay, that's really the problem as I phrased it. Let's find the tension in this rope. If we look at the system consisting of the owner and the rocks, and of course there's the chain or whatever the owner's holding back on, but that's part of the system, so we don't worry about it. This tension in this chain, the chain between the tractor and the rocks, is pulling both the owner and the rocks. And there are two resisting forces, the force of friction on the owner and the force of friction on the rocks. And these are all the forces that are acting on the system. Now, well, there are other forces, but these are the net forces that are acting on the system. The other forces, of course, are the gravitational force in the owner and the normal force of the surface, and gravitational attraction of the earth, or gravitational force exerted on the rocks, and the normal force that supports those rocks. So we can write the situation as follows. The net force acting on the system is the tension in the rope minus the friction 1 minus the friction 2. Now, friction 1 and friction 2 are each going to be calculated by the normal force multiplied by the coefficient of friction. The normal force on a 250 kilogram individual will be equal to the weight of the individual. 250 kilograms times g, multiplied by 0.8 then to get the force, the frictional force F1. So coefficient of friction times the weight of the individual. Since in this case the weight is equal to the normal force, or we'd rather say the normal force is equal to the weight. The normal force on the sled is equal to its weight, 1,500 kilograms times g, and we multiply that by 0.3 to get the frictional force F2. And then we see that, of course, the net force is the mass times the acceleration of the system, and the mass of the system is the total mass of the two objects, the sled and the individual, 1,750 kilograms multiplied by 0.7 meters per second squared. So, taking this somewhat arduous equation here, this expression equal to this expression, multiplying everything out, we can easily solve for the tension, and we get a tension of approximately 7,500 newtons.